Hello students. Welcome to Swami Vivekananda Group of Institutes, the official YouTube channel of Sri Ramakrishna Institute of Science and Technology and Swami Vivekananda Institute of Science and Technology. In our previous video, I discussed about electric charge in detail. In case you missed the video, I will leave the link of that video in the description. In today's video, I will discuss Coulomb's law and the units of charge. I will divide this video in two parts. In the first part, I will discuss the Coulomb's law in detail, important concepts related to this law, the vector form of this law, and its significance. In the second part, I will discuss the concept of unit charge in various systems of units, and dielectric constant of a medium. So, without any further delay, let's jump in today's lecture. We know that, like charges repel each other. If we bring two positively charged particles, or two negatively charged particles, near each other, they repel each other. So, there is a repulsive force acts between them, and the force on each particle is directed away from the other particle. If the particles are free to move, they move away from each other. On the other hand, we know, unlike charges attract each other. If we bring one positively charged and one negatively charged particles near each other, they attract each other. So, there is an attractive force acts between them, and it is directed towards each other. If the particles are free to move, they move closer to each other. Remember, this force of repulsion or attraction between the charged particles is called an electrostatic force. This force is due to the charge properties of the particles. Now the immediate questions that arise here are, how much repulsive or attractive force exists between the charged particles? Which means, what is the magnitude of either of the two forces? And how can we calculate it? Let me explain. The famous French physicist Charles-Augustin de Coulomb first successfully calculated the repulsive force between like charges and the attractive force between unlike charges. In 1785 AD, he put forward his famous law, which we call Coulomb's law. Now the question is, what does this law do? Well, it calculates the force of attraction or repulsion between 2 point charges. He performed several experiments to measure the force of attraction or repulsion between 2 point charges with the help of a torsion balance. Remember, torsion balance is an instrument to measure very weak forces. Before going deep into the law, first let us know one of the three most important concepts of this law. What is meant by point charge? If we go by definition, we get the following statement. A point charge is a hypothetical charge located at a single point in space. It sounds a bit complicated, right? So, let us try to understand it in a simple way. The definition wants to tell us that a point charge is that electric charge which is considered to exist at a single point and thus having neither area nor volume. But this is impractical. So, let us try to have a practical understanding of point charge. Remember, point charges are actually charged bodies of sizes that are negligible compared to the distance separating them. So, we are basically talking about the point bodies. Let us try to understand what are point bodies. Consider the revolution of Earth around the Sun. In this view, you are able to see the entire solar system, and you can now consider the Earth as a point body. This is because the size of the Earth is negligible compared to the distance between the Sun and the Earth. Take another example. If we observe the stars on the night sky, they are the best examples of point bodies. Stars are not small, rather, they are extremely large. However, due to larger distance, they appear as points in the sky. So, we have now understood what is meant by point charge. Simply remember, point charges mean when charges appear as points from a larger distance. In this section, I will discuss the Coulomb's law in detail. We already know that Coulomb's law calculates the electrostatic force between 2 point charges. To calculate the magnitude of this force, Coulomb considered two stationary point charges, say Q1 and Q2, separated by some distance, say r. So, there is electrostatic force of interaction between them. He varied the magnitudes of the charges and the distance separating them, and from his observations, propounded his famous law. He found that if the distance between 2 point charges remains constant, the magnitude of the electrostatic force of interaction between 2 point charges is directly proportional to the product of their magnitudes. So, mathematically I write F proportional to Q1, Q2, if R is a constant. I mark this equation as equation 1. He also found that if the magnitudes of the two charges remain constant, the electrostatic force of interaction between them is inversely proportional to the square of the distance separating them. So, mathematically I write F proportional to 1 upon r squared if Q1 and Q2 are constants. Let this be our second equation. Now combining equations 1 and 2, mathematically, I can write F proportional to Q1, Q2 upon r squared. To replace the proportionality sign with an equal sign, I need to introduce a proportionality constant. So, I write F is equal to lowercase k times Q1, Q2 upon r squared. Let us make this equation our base equation, which can be treated as the mathematical form of Coulomb's law. Here, lowercase k is a positive constant of proportionality, known as Coulomb constant. It is also called the electrostatic force constant. Remember, it is not a universal constant, rather, its value depends upon the following two parameters. Number 1, nature of the intervening medium, that is, the medium separating the charges, and number 2, system of units chosen. System of units means SI, CGS electrostatic system, etc. Now, I will try to find out the value of Coulomb constant. When the 2 point charges are placed in free space, that is, vacuum or air, and the chosen system is SI, the Coulomb constant, K, is found to be equal to 1 upon 4 pi epsilon 0. Here, epsilon 0 is a constant, known as the permittivity of free space. Its value is 8.854 times 10 to the power minus 12 Coulomb squared per Newton meter squared or farad per meter. So, the value of Coulomb constant for vacuum or air in SI system is approximately equal to 9 times 10 to the power 9 Newton meter squared per Coulomb squared. Now the question arises as, what is permittivity? Well, permittivity is a property of a material that measures the opposition it offers against an electric field. So, it is basically a description of the ease with which an external electric field can pass through a given material. Remember, if a material is observed to have a high permittivity, this indicates a better resistance to an external electrical field. So, in SI system, for vacuum or air, the mathematical expression of Coulomb's law is F is equal to 1 upon 4 pi epsilon 0 times Q1, Q2 upon R squared. We have just learnt the mathematical expression of Coulomb's law in SI system for vacuum or air. Let us now consider the charges are situated in a medium other than free space. Will there be any change in the previous expression? Well, the answer is yes. When the 2 point charges are situated in a medium other than vacuum or air, and the SI system is chosen, the Coulomb constant K can be expressed in the following two ways. The first one is K is equal to 1 upon 4 pi epsilon. We can also write K is equal to 1 upon 4 pi epsilon 0 K. Note that the letter K in the denominator is uppercase K. The term epsilon is known as the absolute permittivity of the intervening medium. Remember, absolute permittivity of vacuum or air is a minimum, and its value is equal to the value of epsilon 0. Now, if we compare the two expressions of Coulomb constant, we get the following relation: epsilon is equal to epsilon 0 times uppercase K. So, the uppercase K denotes the ratio epsilon upon epsilon 0. This ratio is also denoted by epsilon suffix r. Uppercase K is called the dielectric constant, while epsilon suffix r is called relative permittivity of the intervening medium. I will discuss this dielectric constant or relative permittivity a bit later in this lecture. Now, back to our current discussion. So, the mathematical form of Coulomb's law in SI system for any medium other than free space or air is F is equal to 1 upon 4 pi epsilon times Q1 Q2 upon R squared. Or, you can also write F is equal to 1 upon 4 pi epsilon 0 K times Q1 Q2 upon R squared. So far, we have considered only the SI system of units. There is another system of units known as CGS electrostatic unit. In this system of unit, the value of 1 upon 4 pi epsilon 0 is equal to 1. So, for medium other than vacuum or air, the value of Coulomb constant in this system of units is equal to 1 upon uppercase K. So, in CGS electrostatic system, for medium other than free space, the mathematical expression of Coulomb's law is given by F is equal to 1 upon uppercase K times Q1 Q2 upon R squared. If the medium is vacuum or air, then the expression simplifies to F is equal to Q1 Q2 upon R squared, because for vacuum or air, the value of uppercase K is equal to 1. I have told earlier in this lecture, there are three most important concepts related to Coulomb's law, and I have already discussed one of them, which was the concept of point charge. Now I will discuss the remaining two concepts. It is a well-known fact to us now that there is electrostatic force of repulsion and attraction between charges of same polarities and of opposite polarities, respectively. Now the question is, what is the direction of the electrostatic force of interaction between 2 point charges? To find out this answer, we draw a straight line extending through the centers of the 2 point charges. This can be considered as the axis of the 2 point charge system. Remember, the electrostatic force of interaction always acts along the line which passes through the centers of the charges. If we have charges of same polarities, this force is away from the centers of the charges. But, when we have charges of opposite polarities, this force is towards the centers of the charges. These facts are all evident from the two figures. One important information we obtain from this discussion: electrostatic force of interaction is also called the central force. Why is it called so? Remember, the force that acts along the line joining the centers of two bodies is called a central force. The magnitude of central force depends only on the distance between the two bodies. Since the electrostatic force of interaction satisfies these conditions, hence it is called central force. Now the third important concept of Coulomb's law. Coulomb's law is also called inverse square law. Why is it called so? The simple answer is, the electrostatic force of interaction between 2 point charges is inversely proportional to the square of the distance between them. Now, what does this mean? Well, consider this diagram. 2 point charges are separated by a distance r. If I double their separation, keeping the magnitudes of the charges constant, the electrostatic force of interaction between them decreases to 1/4 of the initial value. Now, if I reduce their separation to half of the initial value, again keeping the magnitudes of the charges constant, the electrostatic force of interaction between them increases by 4 times. So, the magnitude of this electrostatic force of interaction varies inversely with the square of the distance between the 2 point charges. Till now, I have only discussed the expressions which enable us to calculate the magnitude of electrostatic force of interaction between 2 point charges. As we know, force is a vector quantity, so, in this section, I will discuss the vector form of Coulomb's law. I will divide this section of the lecture in 2 parts. Consider 2 point charges, Q1 and Q2, placed close to each other, and the charge Q2 is free to move. Since the 2 charges are of same polarities, hence, they repel each other. As a result, the charge Q2 is displaced. In the first part, I will express the force on Q2 provided by the charge Q1 in vector form. The charge Q2 experiences the force applied by Q1 in this direction. I denote this force as vector F suffix 21. So, vector F suffix 21 represents the force on charge Q2 applied by the charge Q1. Due to this force, the charge Q2 is displaced away from the charge Q1. I denote this displacement as vector R suffix 12. So, vector R suffix 12 is the displacement of the charge Q2 away from the charge Q1 as shown in the figure. To find out the expression of the force in vector form, I will use the concept of unit vector. A unit vector, say A hat or A cap, can be expressed as A hat is equal to vector A upon its magnitude, that is, A, where A hat is the unit vector in the direction of vector A. So, vector A is equal to its magnitude A times A hat. So, any vector can be expressed as a product of its magnitude and a unit vector in its direction. Using this analogy, I write force vector F is equal to the product of its magnitude and unit vector F hat in the direction of the force vector. Substituting the expression of the magnitude of the force, we get vector F suffix 21 is equal to 1 upon 4 pi epsilon 0 times Q1 Q2 upon R squared times R suffix 12 hat. You will get this expression in your books. But have you ever noticed? You are considering the force vector F suffix 21, but you have the unit vector R suffix 12 hat on the right hand side of the equation. Shouldn't it be the unit vector F suffix 21 hat on the right hand side of the equation? Let me explain it. Here, I put the unit vector F suffix 21 hat in place of R suffix 12 hat. Before moving further, let me tell you what a unit vector actually is. Well, a unit vector is a vector of unit magnitude which is used to indicate direction. So, you must remember that magnitude of every unit vector is always 1 and it indicates only direction. So, R suffix 12 hat is the unit vector of vector R suffix 12 in its direction. Similarly, F suffix 21 hat is the unit vector of vector F suffix 21 in its direction. Magnitudes of both the unit vectors are equal to 1. Now, listen carefully. Unit vector of the force and the unit vector of displacement are the same, that is, F suffix 21 hat is equal to R suffix 12 hat. This is because they have the same magnitude and direction. So, instead of the unit vector of force, I can put the unit vector of R in the equation. Hence, vector F suffix 21 is equal to 1 upon 4 pi epsilon 0 times Q1 Q2 upon R squared times R suffix 12 hat. Let this is our equation A. Now the second part of this topic. Here I will express the electrostatic force on charge Q1 in vector form. To do so, first I make the charge Q1 free to move. The charge Q2 exerts repulsive force on charge Q1 in this direction. I denote this force as vector F suffix 12. So, vector F suffix 12 is the force exerted by charge Q2 on Q1. As a result of this force, charge Q1 is displaced away from Q2 in this direction. I denote the displacement of Q1 as vector R suffix 21. So, vector R suffix 21 is the displacement of charge Q1 away from the charge Q2. Using the previous logic, the vector form of the force acting on charge Q1 can be written as vector F suffix 12 is equal to 1 upon 4 pi epsilon 0 times Q1 Q2 upon R squared times R suffix 21 hat. I mark this equation as equation B. I place our equation A and the diagram of the first part on the screen. Now compare these two diagrams. Since R suffix 12 hat is the unit vector in the direction of the displacement vector R suffix 12, as per the figure, this unit vector is directed from left to right. But R suffix 21 hat is a unit vector in the direction of the displacement vector R suffix 21, and hence it is directed from right to left. So, what is the relation between these two unit vectors? Well, they have the same magnitudes, but are oppositely directed. So, I write R suffix 12 hat is equal to minus R suffix 21 hat. The negative sign indicates that they are oppositely directed, while the equal sign signifies they are equal in magnitude. Substituting this in equation A, I write vector F suffix 21 is equal to 1 upon 4 pi epsilon 0 times Q1 Q2 upon R squared times minus R suffix 21 hat. Now I change the position of the negative sign and write vector F suffix 21 is equal to minus 1 upon 4 pi epsilon 0 times Q1 Q2 upon R squared times R suffix 21 hat. Consider the terms within the second bracket on the right hand side of this equation. It is nothing but vector F suffix 12 as per the equation B. So, I get vector F suffix 21 is equal to minus vector F suffix 12. This means that the two charges exert forces of same magnitude on each other, but in opposite direction. Thus, these are Newtonian forces, that is, forces of action and reaction. So, Coulomb force acts in action-reaction pair. I will now discuss the significance of Coulomb's law. Theoretically, the range of Coulomb's law is infinite. This is because it obeys the inverse square law. But in practice, there is a specific range over which the Coulomb's law holds good. Remember, Coulomb's law holds over a large range of distance, starting from 10 to the power minus 14 meter to a few kilometers. This law helps us to explain the force which acts between the electrons and nucleus of an atom. This law also helps us to explain the force which binds the atoms, or molecules of matter, and holds it together in the liquid and solid phases. Here are some points you must remember about the Coulomb's law. Number 1. Coulomb's law can't be derived because it is based on physical observation. Number 2. This law holds good only for point charges. Number 3. Coulomb's law is analogous to Newton's law of gravitation with some differences. I will discuss this later. Number 4. Like gravitational force, Coulomb force is conservative in nature. Number 5. Coulomb force acts in action-reaction pair. We have already proved this during the discussion of vector form of Coulomb's law. Number 6. The magnitude of Coulomb force does not depend on the polarity of the charges. This means, if we place two like charges, and two unlike charges of same magnitudes, in the same medium, separated by same distance, the magnitude of Coulomb force, in both the cases, will be the same. Number 7. The electrical force, between two-point charges, is independent of the presence of other charges. That is why, Coulomb force is a two-body interaction, and we can apply the principle of superposition. Number 8. Coulomb's law is valid only when the separation between charges is greater than 10 to the power minus 15 meter. Because 10 to the power minus 15 meter is the order of the diameter of nucleus, and so, for distances less than 10 to the power minus 15 meter, nuclear forces come into play and dominate all other forces. Remember, there are some limitations of Coulomb's law as well, like distance between the two-point charges must remain constant, and charges should not be accelerated. Now, the second part of this lecture. Units of charge and relative permittivity, or dielectric constant. I will now discuss the units of charge. To discuss this, we need to define what is unit charge. For this purpose, I am writing the mathematical expression of Coulomb's law for both SI and CGS electrostatic system. We know that when the medium is vacuum or air, and the chosen system is SI, F is equal to 1 upon 4 pi epsilon 0 times Q1, Q2 upon R squared. If the chosen system is CGS electrostatic system, then for the same medium, we have F is equal to Q1, Q2 upon R squared. This is because the value of dielectric constant is 1 for vacuum or air. Note that, in order to define unit charge, I need to find out that condition from both the equations, for which I will get the magnitude of both the charges equal to plus minus 1. The question is, how can this be done? Here I will teach you some simple tricks with which you will be able to define unit charge with ease. First, I am writing the general mathematical expression of Coulomb's law, irrespective of medium and system of units. F is equal to K times Q1, Q2 upon R squared. Now, note the following steps carefully. Step 1. Make both the charges equal in magnitude. So, I am considering both Q1 and Q2 are equal to Q. Step 2. Choose the value of F in such a manner that it can cancel out the value of Coulomb constant, that is, K. So, I write modulus of F is equal to modulus of K. The modulus sign I have used here to indicate that only the values of F and K are equal. Step 3. Make the separation R equal to 1. So, R is equal to 1. Now, if you put all these conditions in the above equation, you will get K is equal to K times Q into Q upon 1 squared. From this, we get Q squared is equal to 1. Therefore, Q is equal to plus minus 1. So, we have defined unit charge. Remember, I will apply these steps to define unit charge in both SI and CGS electrostatic system. First, I will consider the SI system. In SI system, unit charge is known as Coulomb, denoted by uppercase C. In this system of units, for vacuum or air, the mathematical expression of Coulomb's law is F is equal to 1 upon 4 pi epsilon 0 times Q1, Q2 upon R squared. We know that 1 upon 4 pi epsilon 0 is equal to 9 times 10 to the power 9 Newton meter squared per Coulomb squared. So, the above equation can be written as F is equal to 9 times 10 to the power 9 times Q1, Q2 upon R squared. I mark this expression as equation 1. Let both the values of Q1 and Q2 are equal to Q. R is equal to 1 meter and F is equal to 9 times 10 to the power 9 Newton. If you put all these values in equation 1, you get 9 times 10 to the power 9 is equal to 9 times 10 to the power 9 times Q into Q upon 1 squared. This leads to Q squared is equal to 1. Hence, Q is equal to plus minus 1 Coulomb. So, I define 1 Coulomb as follows. 1 Coulomb charge is that charge which, when placed at rest in vacuum or air at a distance of 1 meter from an equal and similar stationary charge, repels it and is repelled by it with a force of 9 into 10 to the power 9 Newton. Now, the CGS electrostatic system. In this system, unit charge is known as stat Coulomb or ESU of charge. In this system of units, Coulomb constant is equal to 1 upon uppercase K, which is the dielectric constant of the given medium. So, for any medium, the mathematical expression of Coulomb's law is F is equal to 1 upon K times Q1 Q2 upon R squared. The value of dielectric constant for vacuum or air is 1. So, we have F is equal to Q1 Q2 upon R squared. I mark this expression as equation 2. Let both the values of Q1 and Q2 are again equal to Q. R is equal to 1 centimeter and F is equal to 1 dyne. If you put all these values in equation 2, you get 1 is equal to Q times Q upon 1 squared. This leads to Q squared is equal to 1. Hence, Q is equal to plus minus 1 stat Coulomb. So, I define 1 stat Coulomb as follows. 1 stat Coulomb charge is the charge which, when placed at rest in vacuum or air at a distance of 1 centimeter from an equal and similar stationary charge, repels it and is repelled by it with a force of 1 dyne. In the final topic of this lecture, I will define relative permittivity or dielectric constant of the medium. The relative permittivity or dielectric constant of a medium is the ratio of absolute permittivity of the medium to the permittivity of free space. So, epsilon suffix r or uppercase K is equal to epsilon upon epsilon 0. Let us now express dielectric constant or relative permittivity in terms of forces between electric point charges. In SI system, for vacuum or air, the mathematical expression of Coulomb's law is F suffix 0 is equal to 1 upon 4 pi epsilon 0 times Q1 Q2 upon R squared. Let this is our equation 1. For any medium except free space, F is equal to 1 upon 4 pi epsilon 0 K times Q1 Q2 upon R squared. Suppose this is our equation 2. Dividing 1 by 2, we get F suffix 0 upon F is equal to K. So, the dielectric constant or relative permittivity of a medium is the ratio of the electrostatic force between two charges separated by a certain distance in vacuum to the electrostatic force between the same two charges separated by the same distance in that medium. Remember, if you replace the dielectric constant, that is, uppercase K, by epsilon suffix r, you will get the definition of relative permittivity. Students, this concludes our today's lecture video. See you in the next video.